Hello everyone and welcome back to Terabyte. We are Geek Gurus Union and this is the third demo video. So last time we introduced Terabyte, a crop prediction system that provides data-driven solutions to farmers. In this demo video, we'll provide an update on our documentation, machine learning model, testing and overall progress of the project.
So for our functional requirements, we focused mainly on the field management subsystem, the user management subsystem, the crop prediction model subsystem. We'll dive deep into these as we progress throughout the demo.
As we can see, this is on our architectural diagram. It uses layered MVC, client, server, and pipe and filter. We'll go into more depth in the next page. So for our architectural patterns, we use four. We use layered, MVC, pipe and filter, and client server patterns. For the layered, it is divided into three layers: the presentation layer, the business logic layer, and the data layer. The presentation layer uses the client view, which is our user interface. It sends requests down to the server, which is on the business logic layer controller, and the controller sends the request to the model, which chooses the appropriate service to use and model data. The model also interacts with the database and it sends it back to the controller. The controller sends the response back to the client or the server view and sends it back to the client view for representation of data. Next, we have explained the MVC pattern in the layer as well. So let's talk about pipe and filter. Our field CRUD service in the model uses the pipe and filter pattern. The first service it uses is an external weather service. Field coordinates are sent to this service, and from there data processing happens. It takes the field coordinate data, it gets the data, it filters the data again, and returns the filtered data back to the model. The next pipe and filter filters the weather data and gives a generative AI summary. The next pattern is client-server, where our application is split into a client and a server.
Due to the significant role that testability plays in our project, we spent quite a bit of time ensuring our system works smoothly as it's supposed to. For our unit tests, we made use of ViTest and got a coverage of about 80%. We also began end-to-end testing using Cypress, which is still in progress, but we do have some working tests already.
So for the backend test and code cov, we achieved a 62% code coverage for all of our unit tests. We have automated all of these tests and we worked on ensuring a reliable interface in the backend, which is part of the testability quality requirement. For the integration tests, we mainly used Postman and ViTest to ensure that not only the correct data is returned, but also the correct format, and everything else that is needed for the testing quality requirement.
In our CI/CD pipeline, we use GitHub Actions to automate all testing and deployment processes. These key components include assertable tests, to ensure the API is up and running, backend deployment, backend integration tests, backend unit tests, and continuous integration. And then last, we also have the front-end unit tests.
As we can see from last time, the UI looks completely different. This was a decision made by the team to improve the overall user experience and to have a better user interface. On the left-hand side, we can see a field card. It has a drop-down to select your field, an expected yield value for the selected field, the hectare, and an unknown button which will change to the field health status. Right under that, there's an AI weather summary, which gives an AI weather summary for the selected field conditions, a field health chart, a precipitation and sprayability chart, and on the bottom we have another panel that you can open to view even more statistics about a field. If we select a field from the drop-down, we can see that the whole interface changed dynamically. On the right-hand side, we have the Google Maps field map, and on this field you can also click on the other maps or the other fields on the map to change the data dynamically. As we can see, this field health chart has a prediction of 7 days over all the healths. Scrolling a bit down, we have the precipitation and sprayability chart with data, and this is interactable as well. We can click on sprayability to show only the precipitation, and the other way around as well to only show sprayability. Clicking on any of these help menu buttons will open a view which you can view more information about the graph as well. If we scroll a bit down, we can see even more statistics which include the soil moisture, soil temperature, dew point, humidity, pressure, and UV index. The redesigned version of this gives you more in-depth specifics of a certain field instead of just an overall overview of the system and your fields.
For a more accurate representation, we have introduced crop stages. The reason for this being that different variables differ over time. If we take the whole year in one perspective, it won't be an accurate prediction. As on the next slide, you can see how the cloud cover, for example, differs over the different stages for wheat for our current case study. We are still investigating this and will continue to improve the model as more data arrives.
Okay, so we have researched different type of IoT devices that we could possibly use, and we've decided to go with a 7-in-1 soil sensor, which means we will measure the core data that we will need in order to make predictions using the data received from the sensor. This data includes the NPK, which is also known as the nitrogen, potassium, and phosphorus, which is the most crucial in crop growth. To receive the data from the sensor, we use a RS485 to USB converter. It is possible to get a RS485 to Wi-Fi converter, but for a proof of concept, we've decided to stay with a USB component. Once we receive the data from the sensor, we will be able to sort it in a Python program and then send it to the AI model to give up-to-date predictions and whatever is necessary. And then we will also use UP sensors as a measure to evaluate and compare our in-house sensor performance and make accurate yield predictions.
Okay, so what's next for Terabyte? Our next iteration will improve upon the beta version by implementing real-time IoT sensors, improving on what we've built so far, and introducing team management. Thank you, everyone.